Okay, by the way, there's something fundamental we're doing here that is going to be important for what we want to think about. We're going to talk about time frequency analysis, right? And here's the big idea that we're going to think about with Fourier. Fourier says we can represent things as sines and cosines. Well, big deal. Why does that help us, right? When we think about this, we're going to think about this f of x as being a time signal. And what this Fourier transform allows us to do, or this Fourier expansion allows us to do, is to say, well, actually, what I'm going to do is I'm going to replace representing this function in the x domain by representing it in terms of collections of cosines and sines. And in fact, what I care about are the c of n, the coefficients, okay, here. So for instance, c1 corresponds to n being 1 here. Maybe I'll illustrate it actually over here. This is a little simpler. Think about what these mean right here. If I think about what the A1 represents, A1 represents cosine x, right? So cosine x has a certain frequency. So what I'm doing is replacing my x dependence by a bunch of frequency content. So I have cosine 1x, cosine 2x, cosine 3x, cosine 4x. As n gets higher, it's higher and higher frequencies. So what I want to do is take a signal in time and simply replace it by a representation of the signal as a collection of frequencies components. Okay? So by the way, when you hear a bird chirp, if you have a detector for bird chirpers, right, you would see its frequency content. You're seeing its Fourier transform. You're not seeing the pressure wave and how the signal is changing in time. What you see is what is the spectral content of that bird chirping. Okay? That's what you look at when you typically do audio engineering. Frequency content. You always take the signal and you always represent it in terms of frequency content. And how do you do that? Fourier transform it. Okay? That's the role this is going to play. It's a different representation of the signal. Okay? We're going to work with that a lot. Because part of what we want to do is start thinking about, if I represent this in the frequency domain, what does that buy me? And it turns out, like for instance, in radar problems, it buys you a ton. So that's what we're going to talk about Friday. Okay, questions on that so far? Yeah?
So f of x is an arbitrary function. It's not periodic on minus L to L, or you just, what's the relationship?
Yeah, so typically, this is defined. The way we think about this is you say, look, suppose this is defined on negative L to L. And let's just say this is some function like this. That's my function f of x. What the Fourier transform or the Fourier representation, Fourier series does to do this, it says, well, actually, this is a periodic function, is it not? It's just that it takes this thing here and I should have drawn an easier function. And it makes a periodic extension of it. Now, typically, we're only interested in this domain here. But technically, what it does is it's valid from negative infinity to infinity. And what it does is creates a periodic extension. And at discontinuities, you see one right there, it takes a value halfway between as you sum to infinity. By the way, nobody in this class is going to sum to infinity. I know, you'd be here for a long time. Okay? All right. We're not summing to infinity. You always say, yeah, infinity's big, right? So let's just take something big and call it good. Okay. So that's going to be the idea of the Fourier transform. Okay? Now, by the way, what else are Fourier transforms good for? Let me show you. Actually, I'm going to skip that because we want to get to there's some nice properties it has that we'll address later. But for right now, I want to make a couple comments about this here. This exists in MATLAB. You want to take a signal or a function and turn it into frequencies. Okay? You would define it some f. Suppose you have a vector f in MATLAB. Actually, let's not call it f. Let's call it, suppose I have u. I have some function u defined. If I want it in the transform domain, All I got to do in MATLAB is say the following. Let's call it UT for U transform is. See how easy that is? Nice. FFT stands for fast Fourier transform. Now, why not just call it the FT? Right? Seems a little bit bragging to call it the FFT. Like, oh, I'm super fast. Well, it turns out they can brag. Because this operation here, one of the couple comments I want to make about this, we're not going to go into too much detail about it, but when you do the FFT, FFT was kind of invented in the late 60s by Tukey and Cooley. Now, picture yourself in the late 60s. Long hair, tie-dye, maybe you show up to class, having a drum circle afterwards. Okay, but at that time, computers were slow. My iPhone over there would be like the mega computer of the world. 1968. Okay, so given that, these guys were trying to actually compute pretty important things. Oh, I mean, depends on what you think is important. But for instance, one of the big pushes in computational science came from Los Alamos when they were trying to actually compute pressure waves to create bombs. Okay? That's a slow computation. It's 3D, PD computation, and extremely slow. Anything you can do to speed up your code would be greatly appreciated. Okay? And generically, when you would compute this would be something like whatever the size of your vector you're working with here, it costs you order n squared to do this. Well, Cooley and Tukey came up with an algorithm that said, well, actually, I can do that in n log n. By the way, if you can beat n log n, you'll be famous. Okay? You will. Guarantee it. Promise you. I'll give you more than 25 cents if you can do it. Okay? Give you $1 and buy you lunch. Okay. So there you go. So what they came up with is this algorithm that's pretty much the standard. That's about as, unless you have a very specific problem with a very specific setup, maybe you can beat this, but for the most part, that's kind of almost like a speed limit. And if you can beat that, you're rocking it. So that's why they added the extra F. Okay? It's a fast Fourier transform. And we're about to use it. A couple things that they came up with, a couple observations. The key to this algorithm is that what it does, it was actually a very simple observation they made. What they found out is because of the relationship among these Fourier coefficients, or these frequency components, what they found out is you could say, hey, you know what, I can take a problem of size n, and I can break it up into two problems of size n over 2. Well, that problem size of n over 2, I can break that up into two problem sizes of n over 4. Right? So you take this problem of size n, two problems of size n over 2, four problems of size n over 4, 8 problems of size n over 8, blah, 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 all the way down to n problems of 1 by 1. Do you know how easy it solves 1 by 1? Pretty easy. Remember, each problem that you solve, whatever size it is, costs you computational speed. So if you're solving the big problem of order n, of size n, it's very expensive. But if I can solve a bunch of 1 by 1s, then I have to just glue my answers back together. And that's what costs log n. It costs me n to solve the n equations of size 1 and log n to glue it all back together. Okay? So that's their big contribution to the world. Okay, so that's what they did, late 60s, fast Fourier transform. And at that point, the algorithm really relied on the fact that when you take this vector u, it is a 2n number of points discretization. Right? So you discretize it into 16 points, 32 points, 64 points, 128 points, however many points, right? But power of 2. So you can always break it down to smaller and smaller problems. Nowadays, that's not so important. You can almost get n log n. There's really fancy ways to do this, like if I use 100 points, right, which is 2 problems of size 50, 4 problems of size 25, right, and then all of a sudden 25. Okay, what I got to do with that? So then, right, so you run a problem. But now they pad zeros in there, and they can pretty much get an n log n speed out. Okay? All right, and there was a hand. Yes?
Fidelity when gluing the solutions back
No.
together?
Exact. Sweet, right? I know.